and welcome to the second class of our hands-on supply chain solver building. I'm Cristina Radu, and we have here Felipe Brandão from AMPL. And today we want to talk a little bit about what's happening in the solver, what is the behind the scenes. Because you start with the business requirements, and then what is the technical path? You start writing equations, they are transformed in different files, they are sent to a mathematical solver, and so on. So we want to clarify what's happening and also give you a practical presentation. Then we will quickly go through what is linear programming, mixed integer programming, constraints programming, and how does optimization connect with AI/ML. And we will discuss heuristics versus mathematical optimization. They are both two very good methods to solve problems. And sometimes it's good to use one or the other, and sometimes together. So let's start. A solver, it's an algorithm that basically you have an input, a set of rules, and you produce an output that satisfies some constraints. And we can split the solvers in mathematical solvers or optimization solvers. And examples would be like Gurobi, Cplex, the type of problems, linear programming, open source solvers like Higgs and SCHIP. Solvers which are defined in terms of logical expressions. And then examples are the SAT solvers, and you can find one in the Google OR. But essentially, an optimization model, you have a math equations, you add them in an equation editor, then a model builder, which transforms the equations into a readable format for the commercial solvers or the open source solvers. And then this whole thing is a problem-specific solver. And this is what we are going to talk about today. We are going to go deep into each of those. And here is a diagram that the solver, we can split it in two phases. You have the model plus the build and the solve phase. In the first one, we have input data, and we also have an equation editor where we can write our mathematical or logical expressions. And then this is picked up by a model builder, which transforms the model into a matrix. And this matrix reaches the mathematical solver, like Gurobi or Higgs that we already mentioned. It solves, so that's the solve phase, and it sends back the output. So this is how it's the structure of a solver in general. And now Felipe is going to explain a little bit about how it happens with AMPL. And then we will show you, so like a little demo of what actually happens in terms of equations, the files, the results, and so on.
Yes, so in this diagram, you can see how AMPL fits in this. AMPL does the model building part, and your mathematical equations or logical expressions you write in your AMPL model. And then when that model is combined with data, AMPL is able to produce a matrix, or in the pure linear case, or it can be more information like expressions in the case of nonlinear problems that are then sent to mathematical optimization solvers like Gurobi, ICE, Express, Yopt, and so on. And after the solvers solve the problem, they produce a solution that AMPL then loads back. I'm going to show you these different steps. Let me share my screen. I think you need to stop sharing. Okay, entire screen. So here is the model. In the model, we have sets and parameters that are going to be holding data. Then there are variables, constraints, and objectives. For the sets and parameters, we need data. And And here is some data that can go into them. So this is for different parameters. These are for indexing sets. Once we have model and data, then we can pick a solver to solve the problem. So AMPL is taking care of loading the model, loading the data, combining them together, and converting that into something that the different solvers are able to solve, and then retrieving back the solution to produce reports. Here we can download a snapshot that combines the model and the data. So this is, once we have this, we are ready to build the model that can be sent to the solver. In fact, the way that AMPL communicates to the solver is using an efficient binary format, so it's not very readable. So I'm going to show here the model, the output model written by Gurobi. So after all transformations are applied, here you have an expanded objective, and here you have various constraints. And this model can be quite different from what was originally written, but we keep a mapping between the original expressions and what goes into the solver, so that once we get a solution for this, which is here, and this is essentially variable values for the various variables that were sent to Gurobi, we need to map it back into what was initially expressed by the user in the AMPL model. We don't only return the solution for the various variables, we also return basis information that allows doing interesting things like zero simplex iterations. And this just happened because it was the second time that we were solving the same problem. So we already had the information about the optimal vertex, and so we did not have to move. It was already optimal and it was done. And that's it. So we get the solution and we go back into the AMPL model that then allows us to access the solution values from the various variables and so on, and produce reports. And that's it.
Okay, thank you. So let me share back my screen. Okay, I need to also edit here. So I just want to add one little thing that the app we presented last time a little bit, and today we just wanted to show the technical behind it. But in the next lesson, we are going to go into the equations. How do you define the sets, the parameters, a little bit of the syntax, and then we are going to start building the model. So now you just need to focus on understanding what's behind in those solvers. And now let's talk a little bit about linear programming. This is a very popular technique in supply chain because, as I explained the last time, the problem of supply chain is the balancing demand and supply, and this is basically linear equation. So then that's how linear programming matches it perfectly. It's a very quick and optimal finding solution. And the most used algorithm is the simplex algorithm. And here I will explain it what happens in two variables. This is, let's say, one of the typical problems that we want to produce or we want to sell bowls and mugs. And they bring a profit. So for a bowl, it's $40. For a mugs, it's $50. And in order to produce them, we have available 40 hours of labor per day and 102 pounds of clay. And then we want to maximize our profit. This is the objective function. And the constraints are written here. And we can see that for a bowl, I use 1 hour. And for a mug, I use 2 hours. So then when I put them together, I should not go beyond 40 hours of labors. And in terms of clay, for a bowl, I can use 4 pounds, and for the mugs, 3 pounds. And my top is 100 pounds of clay. Also, our variables need to be positive, as bowls and mugs are usually need to be positive numbers. And then how is this problem solved? You look at the constraints and you create two hyperplanes. So we have one line, which is a constraint with equality. So x1 plus 2x2 equals 40. And this is, let's say, this line. And the other one, 4x1 plus 3x2 equals 120. It's the other line. And then we take the intersection. And this creates those two lines with the intersection and the axis, x and x1 and x2 axis. It creates convex shape. And then what's the beauty of linear programming and in the simplex method, that we know that in this situation, the solution is always one of the vertices, the extreme point. So basically now you just need to jump from one vertex to another and check which point brings you the biggest profit. And this is what is calculated here. So in 0, it's 0. It's not interesting. In the point C, it's 30 bowls, 0 mugs for a profit of 1,200. In this point is 1,360. And in this point, it's 1,000. So what do? You, even if you have a shape which is full of feasible points, the solution is always in one of the extreme point, and in this case is point B. And this is the solution. And now I will let Felipe explain a little bit about linear, or let's say the simplex algorithm in higher dimensions, and also an alternative method of finding a solution, which is the interior point method.
Okay. So like Christina mentioned, in 2 dimensions, each constraint is going to define one of these lines that define faces of this polyhedron. In higher dimensions, we are essentially defining, the constraints are essentially defining surfaces. And these vertices, they, in their intersections, are possible optimal solutions. Because in the objective is also a surface, so it's going to touch one of these points in the linear case. So simplex can be used to move from vertex to vertex until we reach the optimal point. And once we are there, we have the optimal basis, that basis that allowed to have that solution with 0 iterations, because once you are there, you don't need to move further. This is the classical algorithm, the oldest algorithm that exists for this type of problems. These days, especially for bigger problems, there is the interior point method that instead of moving on the surface across the vertices, you move in the interior in the direction of the optimal solution. And that algorithm has a benefit that it has a polynomial time solution. And therefore, there is a predictable runtime for it. So it can be quite useful in situations where you have very large LPs. So, and I think another thing I could mention here is the fact that all solvers include these different solution methods, and different problems can also benefit from might work better with one method or another. So in some cases, simplex might work better than barrier and so on. It's like especially very small problems. In very large problems, typically barrier is going to be the right solution.
Yeah, so barrier is this one, right? The interior point method. It's also called the barrier method.
Yeah.
Yeah, exactly. That's a very good remark, that solvers have a collection of methods, and then depending on the problem, they choose the one that brings the best solutions.
And user can also choose the right one. Typically, by default, they run all of them in parallel.
Yeah.
But the user can already configure, if they already noticed which one is the best, they can configure to use it.
Yeah, that's true. Thank you for that. A few comments about the mixed integer programming. So what is the biggest difference, right? I explained in the previous case. So when we have a linear programming, we have a convex shape, and all the points inside are feasible points, and we know that the solutions are the extreme points. And mixed integer programming means that the solution is an integer. So this means that the space of possible solution is not all of this shape, but only a few points inside. And as we see, they don't always match an extreme point. Like in this case, this is the solution. It's on one of the edges. So in this situation, the algorithms change because we cannot just look for the path from like jumping from one vertex to another. We need to find other algorithms. And here it becomes a bit more complex. What happens is that you usually start with the LP relaxation, and then you start to cut planes. So you start to cut from your shape, try to make it smaller. And another method is branch and bound, where you start with the LP relaxation. For example, if you have a solution which is 3.5, which is not an integer, then you start going on the branch 3 or on the branch 4, and then you go and search it in that direction. So those are like very high level explanation for the methods. But what's more important in supply chain, when do we need to use mixed integer programming? When we have network design, so we need to decide, I have a location here, yes or no. So that's expressed in the binary 1 and 0, but in particular, it's in integers. Campaign optimization, we also need to start a campaign, stop a campaign, and it's the same. And also for the lot size. Lot size is you have a minimal lot size plus incremental. So for example, in the increments, you need to use integers to have, for example, your minimum lot size is 50, and then you need to produce in increments of 5. So minimum is 50, then 55, 60, 60, 65, and so on. So for this incremental, you use integers. So the mixed integer programming is very popular in supply chain, and we are going to talk about those two cases in the course. So campaign optimization, we will show you how it's done using mixed integer programming and other methods, and lot size. Okay, what's next? Quick mention about constraints programming. This is very popular or recommended when you have combinatorial problems. And maybe it's not important to find the optimal, but just finding feasible solutions so they respect the logical conditions, and they can give very good results. And they are so you use them for problems like packing optimization, scheduling, vehicle routing, and so on. So it's a very powerful technique, but it doesn't apply for let's say all the kind of problems. In supply chain, most of the time you have linear programming and mixed integer programming, and sometimes this constraints programming. It's not, let's say, so popular yet. And what is the connection between optimization and artificial intelligence? Is that at its core, the way you train machine learning models is using an optimization algorithm. In particular, you actually minimize an error. And in particular, so the steepest edge method is a particular case of this gradient descent, and this is what is used in the simplest algorithm. So how Felipe explained that you have a path on the shape, on the convex shape, and then you use the steepest edge. So steepest means in which direction do you have the biggest growth if you are maximizing, for example, and then you follow that path. So this is just to bring a bit of a connection. Not many people know this, that actually it's still optimization when we talk about AI ML. And I know Felipe wanted to say something.
Yeah. Yeah, because here, even though AI also starts with optimization, in the end, you can also use AI to again help you build your optimization models. So it is into you complete the cycle this way. Start
Yes.
optimization and then you go back to optimization in the end.
Yeah, it's very helpful now to use artificial intelligence to help us with building the optimization model. Okay, and now let's talk about heuristics. Why am I talking about them? Because I gave you the example that for campaign planning, the textbook method is using a MIP. So you use 1-0 binaries to start, stop a campaign. But in particular, in supply chain companies, they have campaign planning and lot size. And you put that when you put them together, the model does not perform well. Maybe this is something we didn't say, that when you go from a linear programming to a mixed integer programming, the performance suffers a lot because the search algorithms take much longer. The solutions are also not always optimal. So then if possible, it's best to avoid the mixed integer programming. And in this course, I'm going to show you how for campaign planning, you can avoid the MIP and use the LP, which is fast and optimal, plus a heuristic. But in some cases, it's better to use just a heuristic, or maybe the only solution is the MIP. So this comes a little bit with the experience that you have. What kind of heuristics do we have? Rule-based and priority heuristics, and computational meta-heuristics. From here, I will just want to talk about the genetic algorithms because I mentioned the constraints programming method. And in one project, I did a packing optimization, and we used two algorithms, so constraint programming and genetic algorithms. And they both had pluses and minuses. And for example, for some customers, the genetic algorithm was giving good results. For another customer, the constraints programming. So again, it's just you have more methods. It depends of the problem, of the size, and what's available, which method you choose for the best solution. And here, a general comparison between heuristics and optimization. And here in the optimization, I included the LP and the MIP. And on the top, we have general remarks. And on the bottom, supply chain, in particular supply chain. What is the difference when you use a heuristic to balance demand and supply, and when you use optimization, so a linear programming to balance demand and supply? In general, heuristics are fast, but there is no guarantee of a global optimum. Whereas for an LP, the search is still very fast. You find a global optimum. With the MIP, the search becomes slower, as I said. And if you want to find a global minimum, the search can be very long, but you can stop the algorithm before and still have a very good solution. And from the supply chain, I will just mention that for the heuristics, the decisions are taken one by one. So you want to match demand and supply. You start with the first demand, and then you search through your network, the supply that matches. And then this goes out, this demand. And then you start with the second demand. But this means that you're already eliminating a part of the problem. So the solution is not optimal, it's suboptimal, and so on. Whereas if you use an LP, the decisions are all taken at the same time. So all the demands are in the solver, and all the supply is considered, all the constraints and everything. And this is the power of the LP in supply chain. But again, depending on the problem, you might need to use a heuristic or an LP and a heuristic and so on. So there are always pluses and minuses. If you're familiar with them and with how you model problems, you can decide which one is best. So I guess that's all for today. The time passed very quickly. What are we going to talk about next time? We are going to talk about the supply chain data structure, because this is the reason we can teach this course, because in supply chain you have a data structure which is quite fixed. So if you go to all the manufacturing companies, all the problems, they have this data structure in common. And then you build a model on this data structure. So no matter the business context and the business requirements and so on, this data structure stands, and you can use it to build any solver, or at least 80% of the solver for any situation. And then, of course, you have custom constraints, but that's only like 20%. And we are going to talk about how do you, again, now we start to personalize for supply chain. What kind of objectives do you have? What are the typical inputs, the typical outputs? And then we start to talk about the variables, the dimensions, and constraints. And as I mentioned, we are going to go back to the app that you will be using to practice your modeling skills. And we will explain a bit of the AMPL syntax. So already in the app, you will not have to worry about this. The parameters, the set, even the constraints are written. You just need to click and choose and so on. But yeah, we are going to still explain a little bit so you become a bit more familiar with this. Felipe, you want anything to add?
No, no.
Okay, so then thank you for watching. Give us your feedback. We are thinking of having a live Q&A session. So this is the second class after the third and the fourth class where we already start modeling, writing constraints, and so on. We want to organize a live session where you can ask questions to me and Felipe. So if you are up for that, leave us a comment or a message, and then we will organize it. So that's it from today. Thank you so much for joining, and we'll see you next time. Bye.